Hi everyone, welcome to our video on lists. Lists are a very complex topic in computer science, especially when you're just starting out. The chapter on lists is quite long and quite extensive. I do recommend still, of course, reading through that and going through all of the different methods that we introduce there and different things that we can do with lists. We're going to go over some of what we talk about in the textbook in these lecture exercises. And I'm going to actually have this be a bit of a longer video because I'm going to go through all of the exercises so that we can cover as much on lists together as possible. But there is going to be things that we just don't have time to cover in these examples. So please read that textbook, do your labs, reach out if you have any questions, because there's lots of different things that we can do with lists. Up until this point in the class, we've been predominantly working with atomic data. So that's data that's just a single value. So think about when we have a variable and we assign it like an integer, that's just one value that's associated with that variable. But oftentimes we want to store collections of data together. And lists are one way that we can do that. And I noticed in your last assignment that some of you were already experimenting with lists and how those could be used to store, say, like collections of coordinates or collections of colors that you want to display, different things like that. There's different kinds of ways that we can store collections of data in computer science. This chapter is just focused on lists. But there are things like dictionaries that you'll hear about later and other more complicated data structures that you'll find out about in second year. So lists are unique because they have a specific ordering to them. There's a beginning of the list and the end of the list. You can think of it just like a grocery list that you'd have when you go to the store. It starts at the top and you work your way down. There's an ordering to it. You can say I'd like the third item on that list or whatever it might be. And that's what we're trying to replicate here in our programming languages with lists. So they're just a way to collect data and have some ordering to that data. In the textbook, we go over some examples of different things that we can do with lists. And so just a very high level overview here. We'll go over these 3 points. So I'm just going to bring over my processing. We talk about creating lists. And so oftentimes when we're creating lists, what we want to do is create some sort of variable that we're going to store that list in. So of course I'm going to use the very creative myList variable, but you could name it whatever you want. Then we use that assignment operator that we've seen a lot in this class already. And then we tell Python that we're making our list by using the square brackets. So this in and of itself is a valid list. And if we wanted to convince ourselves of this, we could do a print and then wrap that type command where we pass in that variable to say, okay, what data type is this myList variable? And if we run this, it comes back and tells us the list. What this is it's just an empty list. So it's a very similar idea to if you had a string and you just had those 2 quotes with nothing in between it. And remember, we knew that was an empty string. We talk about in the textbook how oftentimes we'll want to make these empty lists if we then want to use a for loop to add some data into it. But we could also have a list where we specify the values in it ahead of time. So I'm going to make a second list. It's going to be, of course, called better list because it's better. And I'm going to give it some values. In this case, I'm going to pass it in strings. These strings are my dog's names. Because, I'm just very creative at all times. And with that one too, if we did the same thing here and we took and checked the type of it, I'm just going to switch this over to better list. You can say, computer, what type is that? It's still a list. So we have 2 different ways of making lists. And then we have all sorts of things that we can do to that list once it's created. So we can add data to it, we can access data, we can remove data. Right now I'm going to just do some examples here with my list. So first I'm just going to print it. So I'm just print command and then that variable name in brackets. And then I'm going to add something to it. So to do that, I just say the variable name, then I use that dot or the period, and the append method. Now it's called a method, but it's very similar to a function. It's called a method because it's acting on a very specific variable. So when we have variable name dot and then some sort of function name, that's what we would call a method. Those are just specific types of functions that operate on a specific kind of data. For append, what that's doing is it's adding to the back of the list. So we could add a value in there, and then we could print the list again to see if it got added. So I'm going to just add a second print statement. If I run this now, you'll see my very first print statement, which I get from line 6 here. I get my empty list, and then I call append, and now I get a 2 in it. If I added other things into there after the 2, so I could add in another great number, 42. I could also add in a different kind of data if I wanted. So lists in Python are a lot more flexible than lists in other programming languages, that you don't have to have only the same data type in them. You can have mixed data types. Now if I do this, I would expect to see 2 followed by 42 followed by true. Let's see if that's correct. There we go. So that's how you can add data in. And you don't have to only be using append on an empty list. So you can use it on an empty list as we see here, or you can use it on a list that already has a value in it. So once we do the append once, we know that this has a value in it, and then we can keep adding. You could do the same thing with better list, but you just use better list instead of my list before that dot. We can also access specific data in our lists, and we can do that by something we call indexing. So as we know, computer scientists love to be different. So we start counting at 0, not 1. So if we were looking at this list down here, our very first element in our list would be at index 0, which would be 2. Our second element in our list is at index 1. And our third element in our list is at index 2. So if you're doing your assignment and you get some weird, like off by 1 errors, it probably has to do with indexing. Off by 1 errors are so common in computer science that they literally have that name, off by 1 errors, and they come up quite a bit. So if you're so close in your assignment or your labs and you're like, this is almost there, but it just keeps on selecting the wrong thing, it's probably because the indexing is just not right. So just go recount it and make sure that it's correct. If we wanted to access a specific element, say in my list, I could do print my list, and then we use again those square brackets followed by the index that we would like to access. So in this case, I say I want the first element in my list, or what's at offset or index 0. And if I do that, I would expect it to return 2. And if I run that, you'll see I get 2 at the end there. But you could change that with any value you want. So if I do 2, think in your head, is that going to be 42 or true that comes back? Hit run. Whoever guessed true, ding, 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 you got some bonus points where the points don't matter. So remember, it's always 0, 1, 2. It goes like that. If you try to access an element that isn't in your list, so if you try to say go for 4, something that we don't have an index at, you should get an error. Sometimes in processing, you won't see an error, but you just don't see anything showing up here. This is the computer trying to be helpful. It's not helpful. And this happens, and I know y'all have seen this in your assignments when you're coding things up. It's like, oh, your program was working. Now all of a sudden it doesn't work and it's just gray or something isn't displaying. It usually has to do with whatever you just typed is an error. So if you are trying to print something and it's not showing, it's probably because you're trying to access something that's outside of your list. So that's why it's doing things like that, okay? I'm going to switch this so that it doesn't cause any more problems. We can also remove data from our lists. So if I wanted to, I'm not going to remove things from better list because I'm not removing my dogs from a list. I don't want them to get a complex. But we can remove things from my list. So we can use that my list variable again, and we would use that dot operator. And then there's 2 different methods that we can use to remove data from lists. We can use the remove method, where we then have to pass in the value that we want to remove. So say I wanted to remove 42, and then I can print my list. And that's going to search through our list and try to find that value that we passed in. If it is found, it will remove it. If there's more than one of that value in the list, it's only going to remove the very first one. So we've got to be a little bit careful with that. But you'll see here, once I call it, and then I print it, that 42 no longer exists. if I wanted to instead use what we would call the pot function, that is going to remove a value at a certain index or offset. So if I wanted to remove 42, I would use offset not 0, but 1. And that should give me the same value, or the same list at the end of the day. So you can do things like that. Another quick tip I'll give before we move into the exercises is that we can use that in command to check, to see if something exists in the list. So if I wanted to make an if statement and I wanted to see if rider was in better list, and if it is, I'm going to print dog found. Else I'll print dog not found. Okay. So this is going to check to see if this element exists in this list at all. If it does, it will return true. So we had predominantly been using in our for loops, which we still can do, but we can also use them in our if statements when we're checking to see if something exists in a list. And if we run that, you'll see we get dog found, and we know that's true because rider is the very first thing on better list. All right, so we're going to jump in now to our exercises and start practicing with lists. The very first, what is this, like 6 exercises we have up here are all about building up a solar system. So we're going to put in these global variables into our processing environment, and then we're going to jump into those exercises together. So if I bring this over again, I'm going to just Control All and delete all my list examples. Whoops. And then I'm going to just add in these global variables. So we have planet X is equal to an empty list. Planet Y is equal to an empty list. And then planet diameter is equal to 50. So you'll notice that these the first 2 global variables we have up here are going to be the X and Y coordinates for the center of the planets. So we'll have each offset corresponding to a set of X and Y coordinates. That might not make the most sense right now. It should make more sense as we go through, okay? Okay, so what we're going to do is do our setup function, and we're going to initialize those 2 lists to have these values here. So everything in this first column, all these X coordinates are going to be our planet X list. And then all of these values here are going to be our planet Y list. So what that looks like is just making our setup function as we have in the past. Should almost be second nature by now. I'm going to bring in those global variables that I want. Planet X. Might just do them as a comma. This is one way to save yourself a little bit of typing. You can put all your global variables that you want to bring into a function in the same line after that global keyword. And it's not plant, it's planet. I'm glad I caught that before I tried to start, because I would have for sure left it and then been very confused why it didn't work. That's a classic me problem. All right, we're going to just do our size quickly. So let's just set this up to be pretty big, 500 by 500. And then since space is dark, we're going to make our background black. But of course, I'm just going to run this quickly to make sure it works as expected. If it doesn't work, I'd like to catch that now so that I don't miss it later on. And where is my display? Here we go. Oh, I have so many sketch pads open from all my list stuff. Here it is. So we got our nice 500 by 500 sketch pad. And I'm just going to delete all of these other ones very quickly so I don't have them open and being confused. I'd be seeing all these gray ones and be like, oh, what's going on? There we go. Sorry about all that flashing there. All right, so that's working. Now we're going to just start adding in values to those lists. So we want to initialize them with those values. We could put them up here, but I'm just going to do it in setup because setup runs once anyways at the very beginning. That way, if we wanted to fix things or change things later on, we could do it in this as well. But either or way would work. So for planet X, we're going to use those square brackets again to indicate that we have a list. And then we're just going to copy one after the other these x values. So starting at 250, followed by 100, followed by 400. And they just get separated with a comma. So 250, comma, 100, comma, 400. So when we're looking at this list, 250 would be the x-coordinate for the first planet, 100 is the x-coordinate for the second planet, and 400 is the x-coordinate for the third planet. Similarly for planet Y, we're going to make a new list with our square brackets, and it's going to be 250, 400, 100. So 250, 400, 100. Okay. And again, if I run this now, it just looks like a black canvas because we haven't actually drawn these at all, right? We've just set it up so that we have those two lists. And that's really all this question is asking us. So just initialize those two lists so that there's 3 planets with the following XY coordinates. So now if we move on to exercise 2, we want to write the processing code that's going to draw the planets that are in that list. Our canvas should be black. It already is because we're smart and we know that space is dark. So we preemptively did that. All the planets will have the same diameter that's given by this global variable. The first planet should be yellow, and then all the other ones will be blue. Okay, so I'll bring over my processing again. We know that since we're going to be drawing, we're going to need to do our draw function now. So remember, none of the drawing happens in setup. It's all going to happen in our draw function, which we've used multiple times. Again, I'm going to bring in those global variables, so planet X, planet Y, and then also planet diameter, because we'll need that to draw. We want our background to be black. So what I'm going to do is I'm going to always have redraw the background. If you've noticed that sometimes when you don't include this, your drawings get a little bit fuzzy or blurry, it's usually because it's overriding them multiple times. And if you include the background command at the very beginning, before all of your other like circles and squares and whatnot, or text even, it will just crisp everything up because it's effectively saying, okay, redraw a new picture every single time. The very first thing we're going to want to do is draw the sun. So we'll do that. We know it has to be yellow, so we'll fill it in with a very bright yellow color because I didn't pre-pick a nicer yellow color. And I know that this will generate me yellow. Then I can just draw the ellipse or the circle for that. And what I'm going to do is access those lists that we had specified up here to get the very first values out of them for the X and Y coordinates. So I'm going to do that by indexing. So we would just say the variable name that we want, so planet X, and then to get the first element in that list, we pass it offset or index 0, because remember we start counting at 0. And the same thing for planet Y. We're going to pass in 0. And I'll just make this a little bit bigger here so we can see it all at the same time. And then we use planet diameter to do the diameter of that circle. Planet diameter, planet diameter. There. Very long line of code, but let's just make sure this works. So this should have our circle, our beautiful sun in the middle. Now that we have that, what we want to do is draw the other planets as well. So we could just hard code that. And when I say hard code, I mean do something very similar. So copy this and just change the indices to 1 and then 2. But we could also use a list. And so this is where the power of a lot of what we have learned throughout the course is going to come together. When we have lists, oftentimes what we'll want to do is the same thing to that list over and over and over again. And if we want to do that, the best way to do that would be through a loop. So what we can do is say, okay, we know that the very first planet is always going to be the sun. After that, let's draw all the other planets. So there's multiple ways you can do this. In the solution that we have in the PDF, it does this part separately, and then it does a loop for all the blue planets. We could do a loop for the whole thing if we wanted as well. And if you did that, you just needed an if statement in there to check to see if it was the very first planet. Then you fill it with yellow. Otherwise, you'll fill it with blue. But we'll follow the solution in the PDFs because there's one really cool thing that they're doing in there that I want to emphasize. So if we're going to draw our other planets, draw our other planets. That's not how you spell planets. We're going to use a for loop. And then we're just going to do our fairly default when we're doing for loop, an I in some sort of range. So we're going to make a range, and we want the range to be from the second element in our list all the way to the end. Now with lists, we can use the length command or len command to get the length of that list, and we can pass that into range as well. So if we wanted to start range at 1 instead of 0, how would we do that? If you said use 2 parameters for range, you would be correct. And so when we use 2 parameters for range, remember the first parameter that we specify is where that new range will start. And then we can use that length command or len to get the length of one of our lists. Since both of the lists are going to be the same length, it doesn't matter which one we choose, but that will just return how many elements are in that list. And that will give us a loop that's going to go through all of the things in our list except for the very first one, which is kind of cool. For this, they wanted us to fill the rest of the planets a blue color, so we'll make them blue, and then we'll do an ellipse that's very similar to the ellipse command we have above, but instead of hard coding the indices for our x and y, we're going to use this I value or variable that we have here. Because remember what's happening here is every iteration of a loop, I is getting a new value from range. It's going to start at 1 and it will go to 1 before the length of that list, which will be the very last offset that we have in our list anyways. So we can just pass it in I. The computer will figure out what that value of I needs to be at runtime. We don't need to worry about it. Planet Y, pass it in I again. What we do need to make sure is that this and this are the same. So we wouldn't want this to be like I plus 1 or anything. We want to make sure that whatever we're putting in here is the same for what we're putting in here so that it's picking the corresponding values from the X and the Y list. And we have our planet diameter. And again, I am just typing like it's my first day, even though it's not. And there we go. That will be our ellipse. And that's going to be our for loop. So if we run this now, we should see still our circle that we have in the middle, but now we should see 2 other planets. So if I run this, ta-da, 2 other planets, hooray. That's exactly what we wanted. Okay, so exercise 3 now, we have 2 different things that we want to do here. One is for when we click a mouse, we'll add a new planet to the lists, and then that will effectively, based on how we have it drawn, draw the new planet as well. And when we press the R key, we're going to delete the most recently added planet's coordinate, except if it's the sun. So we'll start with our mouse click and get that working first. So if we're doing something on a mouse click, we know we're going to need that mouse clicked function. So def mouse clicked. And what we'll want to do is when we click the mouse, add in the coordinates of the mouse X and mouse Y to planet X and planet Y respectively. Since we know we're going to be adding into those global lists, we need to bring in those global variables. So global planet X, planet Y. We don't need to bring in planet diameter for mouse clicked because we're not drawing in mouse clicked. All the drawing is going to be happening inside of that draw function. So now when we have that, all we need to do is when the mouse is clicked, add to those lists. And we know how to add to those lists by using that append function. So again, you just put the variable name, in this case, planet X, dot append, and then pass it in whatever value you'd like to add to that list. In this case, because it's the X coordinate list, we'll pass it in the mouse X. And then we'll do the same thing for planet Y. dot append mouse Y. And that should be all we need for mouse clicked. If I run this now, get the same thing out here, and if I click, ta-da! We get planets all over the place. As many as you want in your solar system. It never ends. So that's what we wanted for that one. The second part of this exercise was the key pressed function that we need to implement. So on pressing the R key will delete the most recent planet, except if it's the very last planet. So we always want to leave the sun in our solar system. How nice of us. So again, we'll use that key pressed function that we've used before. And then we'll bring in those two global lists that are keeping track of our X and Y coordinates. So this is what we're going to modify. And then the draw function will take care of actually doing those removals. So we want to check to make sure the key that was pressed was R. So we'll check to see if key is equal to R. Because if it's not equal to R, we don't want to do anything, right? If it is equal to R, we want to remove the last planet. So I'm just going to do it like this and we'll see if this works properly, okay? So we're going to say planet X, and then which remove should we use? Should we use remove? Should we use pop? What should it be? It's a little tricky because in the textbook we only talked about how remove would go by looking for a value and removing that, and then pop we would pass in an index. One thing we didn't mention is that pop can also just be an empty set of brackets, and that's going to remove the very last thing that's in your list. So that's one way of removing something if you just want it to be something generic like the last thing in the list. And we maybe don't know what that index is because that list size can always be changed. So if I run this and I click things in and then I press R to remove, they go away. And does this work? Why is this yelling at me? So it looked like the sun was still there. But what actually happened is the program crashed and it wasn't running anymore. So you can see it here again. If I click, it's working. And then I R. It looks like it's still working, but then if I try to click, no more planets come. And if I look here, I can actually run it and it's not highlighted anymore. So the program silently crashed, and what happened is we had removed that last coordinate from planet X and planet Y, but then we were still accessing that in draw, and the computer just had a total hissy fit about it and didn't tell us. Now remember from the exercise, we said we wanted to keep that very last planet. So we need to make sure that we only call those pop functions if there's more than one element in those lists. If there isn't, then we don't need to call it. So there's lots of different ways we could do this. We could add a second condition with an and into that main if statement. We could add a second if statement down here that checks to see if there's more than one element in the list and then does that. Lots of different things we can do. The solution PDF shows you how to combine them on what would be line 37 here. So I'll show you how you can keep them separate. So if we wanted to check to see if there was more than one element in the list, we would just check the length of one of our lists, either or, because they're the same size, so it doesn't matter. And we check to see if that is greater than 1. If that is, then we can do these pops. So I'll just move them over. Otherwise, it should keep going. Now, if we run this and I remove all of the blue planets and then click again, it shouldn't scream at me silently anymore. It should keep working. So I can still add blue planets. I can remove. And if I try to remove one more before, I couldn't add after. So you'll see this program is still running, which is exactly what we wanted. And I can just continue all day long drawing little faces in my solar system. There we go. So the last part, I think, or is there one more after this? There is two more parts of this. We want to write some processing code that will shift the location of all of our planets by 20 pixels in either the upward direction, the left direction, the down direction, or the right direction, depending on what key is pressed. So we know that since we're pressing keys, that's going to go into our key pressed function. And so we can just add in those checks for each of the different kinds of, excuse me, for each of these different characters as new if statements after this. So we can say elif and then do the condition. We can also do if. In this case, it's not going to really matter which one you choose because it will always only ever be one of them. I like to get into the habit of doing elif. So if I know they're only going to be pressing one key at a time, it could only be one of the 5 keys. So R, W, A, S, or D. So we'll start, and I'm just going to put the skeleton of that whole big if statement in with the conditions checking for the different keys. So if key is equal to W, we'll do something. Elif key is equal to A, we'll do something. Elif key is equal to S, we'll do something. And then the final one is elif key is equal to D, we're going to do something. And what we'll probably do is going to be very, very similar, but it's just going to be changing that direction. And so I want you to think about this, and I'm going to just go back to the slide here, as remembering that we're on a canvas, right? And so we have our point here that is going to be our sun, or whatever it is, our planet. And the center of that is going to have some sort of X value and some sort of Y value. If we wanted to move it up, we are increasing the Y value. And we know that because the X is still staying the same, but the Y value would increase. So we would be adding to the Y list. If we wanted to move it down, and I just goofed this up because I'm so used to the regular Cartesian coordinate system. This is not add. All of you best be yelling at me. I'll change this color to blue here. This is subtracting from the Y because this is 0. I'm so used to my 0 being here, but it's not. This is like 100, right? Oh, goodness. See how easy it is to make mistakes? So if we want to move up, we will be subtracting from the Y. If we want to move down, we will be adding to the Y. If we want to move to the right, we will be adding to the X. If we want to move to the left, we'll be subtracting from the X. So it's very important when we see more complicated instructions like this, that you take a minute to kind of draw through that and work through it. And then you can catch silly errors like I made up here, where I was, oh yeah, if we're moving up, we're adding, of course. But that's just because my brain has been so trained in this kind of a coordinate system where 0 is down here. This is not what we do in processing. Slide is so beautiful. I hope that somebody clicks on this video at this moment and is like, oh wow, just 10 out of 10 on this scribble slide that we got going on here. But so this is what we need to do. So once we have this figured out, effectively what we'll do is we'll make a for loop that goes through the coordinates for either the Y or the X, depending on what way we're moving, and either adds or removes those 20 pixels from them. So if W is going to shift all the planets upwards, then W is going to subtract 20 pixels from the Y. So all we need to do here for W is make a for loop. We know how to make for loops. We already did that in our draw function. We said for I in range, and this time we want to do it to all of our planets, including our sun, so we don't need to include the 1 at the beginning. We could include the 0 at the beginning, but we can also just do the singular value in there because the 0 is effectively the default anyways. So we'll just take our length, and since we're working with planet Y or the Y coordinates, let's just pass in planet Y. Spice things up a little bit, hey? So for every planet in the planet Y list, we're going to take the element that's at our current index. So we say planet Y, then we use the square brackets to index at that specific location. So that's like saying, I want to take this variable and then add something to it. We're doing the exact same thing, but with lists, we just have to use the index with those square brackets to specify which one we want. And as long as this is the same as this, it will be working on the same element. So again, if we're going upwards, we're subtracting y. Then that's going to move everything up. We'll do the same type of loop for A, which is going to shift all the planets left. If we're shifting left, we're subtracting from X. So for I, in range, length, and we'll pass in planet X, since that's the list we'll be dealing with. Even though it's the same size, it wouldn't really matter which one we're doing. Where it does matter is down here when we're actually modifying those coordinates. So we'll say planet X, I, instead of planet Y, I, like you saw above, is equal to planet X, I, subtract 20. And I see I did a mistake. Nobody told me. I didn't hear anyone yelling at me from behind or anything like that. No one's out my window saying, Kim, what's Y? It's supposed to be 20. The computer would have told us when we tried to run it, but we haven't got there yet. S is going to shift everything down, so we're going to add Y to it. So I'm just going to copy this line of code, these two lines of code here, paste them down here, and switch our minus to a plus. And then D is going to shift everything right, so we're adding X to it. So again, copying the one that we had for A, putting it after this, and switching this to an add. Now, if we run this and I made no more mistakes, I can click, I can add, I can remove things, and then I should be able to move my planets around. And I want to make my smiley face and then move it around. Like so. My floaty smiley face in the sky. How lovely. So again, what we were doing here is just in our key press, we had different for loops that were going through our coordinate lists and then adjusting them by a certain number of pixels, depending on which way we wanted to move them. And we figured out what way if we're adding or subtracting and what list by just kind of looking at that coordinate and convincing ourselves, okay, if we wanted to go upwards, what would that actually be changing? Would it be changing an X or would it be changing a Y? And sometimes if this was confusing, it can help to give like real values to it. So draw yourself out your coordinate, make yourself a planet, figure out what the values are for it in X and Y, and then figure out, okay, if I wanted to move it up, what would the new X and Y coordinates be? And you'll see that it is exactly what we did here, okay? So for exercise 5, which is the final part of our solar system builder, we're going to write some processing code that displays the number of planets in the top left corner. And then underneath, the counter is going to display the X and Y coordinates for every single planet on the list. So we can tell that if we're doing something for every single planet in the list, then we're probably going to have some sort of loop in there that's going to be looping through that list. Since we're displaying it, it's going to go into our draw function. It could also go into a separate function that would get called by draw, whatever you prefer. The solution has a separate function. We'll just put it right into draw because I get to make the rules in these videos. Just living on the edge over here. So after we draw our planets, I'm just going to add some space in here for us to work. And this is where we're going to display our planet info. So at the very top left corner, we want to show how many planets we have. So let's get that working first, and then we'll worry about the other parts where we're showing all the other coordinates. So the background is black, so I'm going to fill this with white just so that it stands out. And then we're going to use that text command that we haven't used as much in the class, but remember it's going to show something on the canvas instead of in the console. And what we're going to say is just pass it in a string that's going to be for our count. And we'll pass it in some values. these values, sometimes you might not know what they should be off the top of your head. If it's top left, it can be somewhere close to 0, 0, but you might need to do some trial and error to make it look proper. I get to use the solution values that already exist, so somebody already did that testing for us, which is great. But usually I'd be trying and running things and being like, oh, that's not quite right, or oh, this needs to be adjusted a little bit. And if we ran this like this, all we would see here is that we have this planet count up here now. I wish I could make that text bigger. I'm sure there is a way that I can. I won't worry about that right now. But everything else right now works exactly the same as it did. So nothing else has changed. We just have this here. If we want the value, we'll need another text command. And if we want the count, or how many elements are in those lists that we have, which would be how many planets we have, we can just use that length command like we were using in our for loops. Pass in one of our lists. Doesn't matter which one, since they're both the same length. And that will give us a count of the number of planets we have, because each element in that list corresponds to either an X or a Y coordinate for an individual planet. So because we know that the length of those lists is the number of planets we have. And in this case, we'll just move it over X slightly, but we'll leave it on the same Y. Hopefully that's enough there to give those two a decent number of space in between. Yes, perfect. And now we can test this out. If I click, you'll see that I get more planets added to my thing automatically. And that's because the length will always just be looking at the latest version of that list that we have. And if I R, they get removed. If I move these other keys, nothing else happens, which is exactly what we want. Now we want to integrate underneath these. We want the coordinates to be displayed. So in order to do that, you guessed it, we're going to need a for loop. So we'll have that for I in range length of our list, which we used in all of our other for loops so far in this question. Then we're going to do some text. So we want some text that's going to display maybe the planet number for us, and then followed by those coordinates. That's just going to give us a little bit more information of like, it's just all these coordinates. It's like, oh, planet 1 is whatever, and then planet 2 is whatever. So that could be helpful. So let's try that out. So we'll do a text command. I'm going to add in here planet, and then I'll concatenate that with I. So that should give me, and I said plant again instead of planet. The planet and then the number of that planet. And we will put that at 10 is where we have the other ones over. And then the key here is that we're going to need to use I to figure out our Y value so that we can get them in a list that goes down. The easiest way to do that is to have some sort of starting offset. So we would say maybe our first one, we would want it to be at Y40. And then we multiply that by I. And we can add in other things here. So we could say, oh, we just want to add I to it. If we do this, and I'll show you what this looks like because it's quite interesting. You're going to get a whole bunch overlapped over here. Oh, and it's going to yell at me. It's not happy at me, and I know why. It's because I have to make this a string. It doesn't know how to handle integers getting added to strings. Let's try this again. There we go. So you can see there's some differences in there, but it's really, really, really hard to see what the differences are. That's because, remember, this is only like 0 pixels, 1 pixels, 2 pixels. So oftentimes what we'll want to do is make that difference bigger. We could multiply, and if we multiply, you get much more space over here. But look at all this beautifulness. Get a lot more space, but we might run out of space really quickly too. So there's all sorts of different ones that we can try. The one in the solution suggests using 40 plus I, but then multiplying I times 15 to get what they call the nicest spacing. But, you know, it's all just trial and error. So really whatever you want. I would probably be a little bit lazy and just multiply it by I, honestly. It all works. So we have our labels for our planets, but now we need to add in those coordinates. So we're just going to add in the coordinate for X by indexing the list that holds the x coordinates with I. And then we just need to figure out, okay, move it over a little bit on our x. We'll want it to be the same y. So we can try, say, 30, and then same y, so it's all on the same line. We'll just copy that over and put it there. And we'll do the same thing for x, or for y. Planet y, I. Move that over by 30 again, and take that same y value. And if I run this, oh my gosh, I need to move things over a bit more. So you can see it's all there, but it's all overlapped and not very nice. Okay, so we'll move these over. Let's move this one here at 60, looked pretty good. And then let's make this 90 and then run it. Ah, much better. Yes, yes, yes. That looks much more amazing. And if I move things up, it automatically is shifting and changing those values. And look at, I can make them go off the screen. That's very satisfying. But yeah, you can do all sorts of fun things with that. We can remove, you name it. And if we keep removing, we'll always have that sun left at the end of the day. Okay. So that's all of the code for the planet exercise. It's a lot, and it's a lot to do with lists. Lots of your assignments are going to be this kind of complex now. So try to start your assignments as early as possible when it has to do with lists, so that you have time to kind of work through, practice, get help, etc., etc. Okay? For exercise 6 here, we're asked what's printed into the console by this program. So we have a list here with a bunch of names. We have this variable p, which is initially false. And then we have this if statement. It's saying if Ernie is in class list. So remember what this does is it checks to see if this element exists in this list. So does Ernie exist in class list? Yes, it does. So that would be true. So we would jump into this body of code. Then it's saying, okay, get me the index of Ernie and store it in I. In this case, the index of Ernie is 0, 1. So it's 1. So I, in this case, is going to be equal to 1. Then we have two if statements here. So if I is greater than 0, so if I isn't the very first element in the list, check the element that comes before it to see if that's Bert. In this case, that's Grover, so this wouldn't be true. We wouldn't even go into this statement at all. If I is less than the length of the list minus 1, which would be the very last element in the list, then we want to check the next element to see if it's Bert. And in this case, the next element, so I plus 1 would be 2, which is this one here. Is this Bert? Yes, it is. So P would become true, and we'd print true at the end of it. So effectively what this is doing is it's saying, okay, wherever I find what I'm looking for in the list, check what's before it and what's after it to see if it's Bert. And if it is, we'll print true at the end. If Bert didn't exist before or after, P would still be false, so false would be what is displayed. If Ernie was at the very beginning, we wouldn't be looking at this if statement here, because this condition would be false. If Ernie was at the very end, we wouldn't be looking at this part here, because this would be false. So this is really just an exercise of tracing through and saying, okay, given all these variables, what actually gets displayed? In this case, what would be displayed is true. We have, I think, just this exercise left here. And we're going to be, again, using lists to solve this. We'll work through it together because lists are a bit tricky, so I want to talk through this as much as possible. The police are working on a case. Dun, dun, dun. The suspect's first name starts with a J, and they work with someone named Michael Thornton. We're going to write a function called find suspects, which takes a list of employees and returns another list containing the names of possible suspects. The employees are going to be a list of string where each string is first name, last name. If there's no Michael Thornton in the list, then no one is a suspect. Otherwise, if there is a Michael Thornton in the list, any name that starts with J would be a suspect and need to be returned. One cool thing is that lots of our methods that we use for lists, we can also use for strings. So things like our index, things, is J in a string, we would be able to use that as well. So we're going to build up a solution to this. This is some example input. So in this case, Michael Thornton is in this employee list. So we would expect the output to be both Jason Bourne and Jack Bauer. And I know this is like a movie, but I need to out myself. I don't watch movies, so I don't know the reference. Yes, you can make fun of me. I deserve it. All right. So the very first thing I'm going to do here, this isn't going to be an interactive program. So we're not going to use our setup and our draw. We're just going to have some variables and a function, and then we'll be calling our function with those variables. I'm going to make this employees list, same as what we have in the slide. I'll just type it out here, and it will probably have typos because, you know, I am true to my nature here. Jason Bourne, Jack Bauer. Okay, so that's our employees list. I'm going to move this back and go back to our other slide. We want this function called find suspects. So what I'm going to do is I'm actually going to define that function before this employees bit, because it's going to be an imperative program. How we typically structure that is functions and then the main part of the program. So this will be def find, what was it again? Suspects. And then we'll need to pass it in a variable because we'd be passing it in that employees list. Just to make it perfectly clear what we're working with here, I'm going to call this something different. I'm going to call it sus. I may not watch movies, but I do know what sus is. And I feel proud of myself, okay? So what we're going to do in here is we want to check to see very first if Michael Thornton exists in that sus list. I see I already have a typo in that. So in here, I'm going to say check if Michael exists. And if they do, find all J names and return them. So that's what we need to do. So this first part here is very, very familiar to us likely. It's just an if statement. And remember with lists, if we want to check to see if something's in a list, we just write out the element that we're looking for. And you need to make sure it's spelled correctly, Professor Kim, in the list that we want to search. And if it is, then that will be true. And all of the stuff that we are doing in here will be executed. So if that's true, we want to find all those J names. And then at the very end, we're going to return our J names. Typically, if we're looking for something and then we want to add it to a list, remember we're going to want to start off with an empty list. So I'm going to make an empty list called J names. And it will be empty to start out with, and will be empty if no J names are in the list and if Michael Thornton isn't in our list. And so we could just return this for those cases where it's empty. If Michael Thornton is in our list, then we're going to go through that list to find the J names. If there is a J name, then we're going to append it to our list. So since we need to go through every element, we're going to need a loop. So we're going to say I'm going to put S in sus. If we need to check to see if the very first element has a J in it. We know that that list is strings. We don't want it to match if there's a J anywhere in the name, only if it's the very, very first. We mention in the textbook that you can also index strings just like we do lists. So we can index S0 to get the very first character in the string. If we want to check to see if that's J, all we need to do is that equals J. And if that's true, then we append it to our J names. Now this might feel like, oh my gosh, where did that come out of? That feels like left field. We mentioned it in the textbook, and that's why we're doing this example, because we can do similar things with strings. So when we're combining strings and loops and lists, you can see how much more complicated things are getting. But all this is doing is we have our list of potential names here. So if Michael Thornton's in our list that we pass in, then we go through every name in that list. We check the verse character in each element. If it is J, we add it to our list of names that we're going to return. Now we can check this here by just going after all of our functions and passing in that employees list that we have. So we would say find suspects and employees. Now, if we just do this, it's going to look like our program's doing nothing. So usually you're going to want to wrap this in a print or save it to a variable to do something with it. We'll just put it in a print so we can see what's going on. We run this, you'll see we get 2 names out at the end here. If we wanted to test it, and we put in AJ, this should not be included because J is second. If we run this now, you'll see that it's still not. So it's really, really good to, when you're coding things out, have examples in there that really test out your program to see if it's giving you the true functionality that you want, okay? I know that was a lot. I know lists are a lot, but they are very, very important and they are more tricky. So that's why we did more chapters at the beginning of the course and we're doing less chapters per week now, is so that you can really have a lot of time to practice and work with them. You can come to help hours if you have any questions, if you're struggling with any parts of the labs or the assignments, whatever, we're here to help. And make sure you give yourself lots of time to work on those assignments because it is tricky. It is a new skill that you're learning and we're almost at the end of it. So there's a lot of other information that we also learned over the last 4 weeks, okay? Good luck and happy coding.